This lecture begins the next unit, which covers work and energy. For those of you enrolled in Physics AB, we begin Chapter 6. For those of you enrolled in Honors Physics AB and in AP Physics C, we begin Chapters 7 and 8. However, prior to looking at work and energy, we also have to do a little bit of mathematical background first. That mathematical background requires one of the methods of multiplying vectors together. There are two different ways in which we multiply vectors together. One of those ways is important for our purposes here. Okay, so some mathematical background. Multiplication of vectors. As I said, there are two ways in which we multiply vectors together. This is the important way for our purposes here. Let's say that I have two vectors, an A and a B, and I'm drawing the vectors together like this, such that we can see a geometrical relationship between them, which is this angle theta, like so. And now we define the following. What is referred to as the dot product, it is also sometimes called the scalar product. Dot or scalar product. We write this in the following manner. We have A, and then the dot symbol, and B. Don't write the multiplication symbol, that's something else. Write the dot symbol. That's why this is referred to as the dot product, and we pronounce this as A dot B. Okay, now by definition, A dot B is equal to the following. You take the magnitude of A, multiply it by the magnitude of B, and then multiply it by the cosine of the angle between the two vectors. When we multiply the vectors together in this manner, we end up with a scalar. It's either a positive number or a negative number. There's no direction associated with it, however, and this is then why it's also sometimes referred to as the scalar product. Okay, now exactly what is being multiplied together here? Okay, you can think of it two different ways. For example, let's say that right here is A once again, and here's B, and then here's the angle theta again. Let's say that I think of the definition above as the following. Let's say that I have A dot B is equal to A cosine theta times B. Okay, if I think of it like that, what I'm going to do is I'm going to take A and break it into components. I'm going to break A into a component that is parallel to B, like so, and then into a component that is perpendicular to B, like so. Right here is what I've isolated in parentheses. This right here is A cosine theta. So notice that I'm taking basically the piece of A that points in the same direction as B. This is, by the way, sometimes referred to as the projection of A onto B. I'm taking the projection of A onto B and then multiplying it by B. So I'm basically taking the piece of one vector that lies in the direction of the other vector and then multiplying it by the other vector. You could also, however, think of it like this. Let's say that I write it as B cosine theta times A. Well, if I think of it like that, I'm going to take the same diagram, but now I'm going to take B and break that into components like this. Okay, so here's A, and then here's B, and then once again, here's the angle theta. And now I'm going to take the vector B and break that into components. I'm going to break it into a component that is parallel to A, like so, and a component that is perpendicular to A, like so. And then right here is the projection of B onto A. Right here in green is B cosine theta. So I'm taking the projection of B onto A and then multiplying it by A. So with this type of multiplication, you're basically taking the piece of one vector that points in the direction of the second vector and then multiplying it by the second vector. That is, their magnitudes. Okay, now there's one other minor detail here to examine before we get to a couple of basic problems. If I wanted to, I could just as easily have thought of the angle between the two vectors as the following. Let's say that I consider this as the angle between the two vectors. Okay, here's A, and here's B again. And now let's think of this right here, that is like so, as the angle. In terms of the original angle theta, this angle here is 2 pi minus theta. So now let me go ahead and write the dot product using that angle instead. So then therefore A dot B is going to be A times B times the cosine now of 2 pi minus theta, like so. Do you recognize right here a trigonometric identity? Specifically, it's the subtraction identity for cosine. Here's what happens when I now insert that identity into this calculation. So I'm going to have, first of all, A times B, and I'll put it here in brackets. If you recall the subtraction identity for cosine, it's cosine of the first angle times cosine of the second angle, and then there's a sign switch, plus sine of the first angle times sine of the second. Like so. Once again, this is a subtraction identity for cosine. It's in basic trigonometry. In this case, however, notice that the brackets simplify. First of all, in the first term, cosine of 2 pi is 1. In the second term, sine of 2 pi is 0. And then therefore, if you simplify what's left over, notice that we obtain, once again, the following. So it actually doesn't matter which way you think of the angle. You can think of it as the original angle theta, or just as easily this angle here, and then ultimately through the trig identity, you end up with the exact same result anyway. Usually what we do is we draw the angle if it's less than 180 degrees. That's typically what we do in simple situations. Okay, now, for now, this is just pure math. So let's just take a look at a couple of examples. I have 2 examples for us. Let's take a look at the first one. It says, find the dot product of the following vectors. A has a magnitude of 5 at a 45 degree angle. B has a magnitude of 6 at a 150 degree angle. Both angles are measured with respect to the positive x-axis. Okay, let me do some erasing here. Okay, so here's what we're given in this first example. First of all, A has a magnitude of 5 at a 45 degree angle. B has a magnitude of 6 at a 150 degree angle. However, what we need is the angle between them. So let's go ahead and draw a simple diagram to illustrate the problem. Okay, so first of all, vector A is at a 45 degree angle into the first quadrant, like so. So right here is A, and then right here in blue, we'll say is the 45 degree angle that we indicated. Okay, and then B is into the second quadrant, and it's a little bit larger than A, so let me just go ahead and roughly draw it like this. Right here is B, and then once again, right here in blue, like so, that right there is the 150 degree angle. However, the angle theta in the dot product calculation is the angle between the two vectors. That's this red angle, like so. That's the angle theta that we need. Notice that very simply, it's nothing more than the difference between 150 and 45. So the angle theta there is 105 degrees, and now I basically have everything that I need to calculate the dot product. So A dot B is equal to 5 times 6 times the cosine then of 105 degrees. Okay, notice that the cosine of 105 is a negative number, so just like ordinary multiplication of integers that you've been working with since primary school, it's perfectly fine for the product to be positive or negative. In this case, it's negative. Okay, now I'm in degree mode on my calculator when I calculate this out. So 5 times 6 is 30, and then times cosine of 105. And this comes out to be about negative 7.76, like so. So when you're given a problem such as this, obviously finding the dot product is trivial. However, it's a little bit more involved if instead of giving the magnitude and directions associated with the vectors, instead what happens if they're in component form? That's the second example. Okay, let me erase this example, however, first. Okay, now let me move my file here on my screen. And now let me read the problem to you. It says, find the dot product of the following 2 vectors. So first of all, vector A. Vector A is 6i hat plus 3j hat. And then we have vector B, which is 2i hat minus 6j hat. And now keep in mind that when we calculate the dot product, A dot B, we need 3 things. We need, first of all, the magnitudes of the 2 vectors, and then ultimately we'll have to find the cosine of the angle between them. Now, finding the magnitudes of these two vectors is obviously easy to do. It's just a little bit of Pythagorean theorem with each. So let me go ahead and do so for, first of all, vector A, and then secondly for vector B. All right, so doing a little bit of Pythagorean theorem here, I'm going to have 6 squared, which is 36, and then plus 3 squared, so plus 9, and then take the square root of all of that. Okay, and that magnitude comes out to be about 6.7. And now do the same thing here with B. So let's see, 2 squared is 4, plus 6 squared, so plus 36, and then take the square root of 40. So square root of 40, here we go, like so. And that comes out to be about 6.3. However, we also need the angle between the two vectors. So then therefore, let's draw a diagram here to illustrate and see if we can then use that diagram to find the angle theta. Okay, so first of all, vector A. Vector A is into the first quadrant. So it's like over 6 and up 3, it roughly looks something like that. Okay, and then vector B here is in the fourth quadrant. It's over 2 and down 6. It roughly looks something like that. Right here is the vector B. So the angle theta that I need here in this problem is this angle right here. This here is the angle theta. So how do I find that angle? Well, what I can find, first of all, is the angle that each of the two vectors makes with respect to the positive x-axis. So let's do that first. So right here for vector A, I'm going to go ahead and find this green angle right here. I could do so by using these components. Now, I'm not going to draw the components there in that diagram because it'll get messy if I do. But right here, the adjacent side of the right triangle associated with vector A is 6. And then right here is the opposite side, which is 3. So for this green angle, if I do inverse tangent of 3 over 6, that will then give me that green angle. So let's go ahead and do that. So inverse tangent of 3 over 6. There we go. And that's about a 26.6 degree angle here in green, like so. And then I'll do the same thing for vector B. We'll go ahead and find this green angle like so into the fourth quadrant. We'll ignore the negative sign associated with it. But I can go ahead and find that green angle by noting the components here of B. So once again, I'm not going to draw this because it would be messy if I do. But right here, the adjacent side of the right triangle for B is 2. And then right here, the opposite side of the triangle for B is 6. So this green angle here is going to be the inverse tangent of 6 over 2. All right, so inverse tangent of 6 over 2. And that's about a 71.6 degree angle going down into the fourth quadrant. Like so. Okay, and then we'll just add the green angles together, and that will then finally give me the angle theta after all of that. So 26.6 plus 71.6. This red angle here is 98.2 degrees. And now finally, I've got everything I need. Let's go ahead now and find the A dot B dot product. All right, so we take the magnitude here of A, 6.7, times the magnitude here of B, 6.7, there we go, times 6.3, and then times finally, after all of that, the cosine then of 98.2 degrees. Okay, and then after all is said and done, we end up here with a -6, like so. So as I went through this process, yes, admittedly fairly quickly, you could see that the process is pretty simple and straightforward. It's just a little bit of basic trigonometry, but it's also pretty tedious. I have to go through a bunch of basic trig here to find the magnitudes of these two angles, or of these two vectors, that is, and then do some basic trig here to find these green angles and add them together to find the angle theta between the two vectors. But take a look at this -6. Take a look at the two vectors. Using multiplication, can you get a -6 out of those numbers? Yes, you can. Notice that 6 times 2 is 12. 3 times -6 is -18. 12 minus 18 is -6. Yes, there is a shortcut. Here's how the shortcut works. Okay, now as I initially begin to write out this shortcut, initially it's going to look like anything but a shortcut. Here's what I mean. Let's say that we have two generic vectors in component form. Let's say that we have an A, which is an A sub x I hat, plus A sub y j hat. And let's say that we have a B, which is a B sub x I hat, plus B sub y j hat. Okay, let's just go ahead and multiply those together. So A dot B. Okay, so A sub x I hat plus A sub y j hat dot B sub x I hat plus B sub y j hat. Okay, and this is where it starts to look a little bit long-winded, because what I have to do here is I have to FOIL this out. All of the ordinary rules of multiplication that you're familiar with from ordinary scalar multiplication from primary school, all those rules still apply here as well. So let's go ahead and take this term and multiply by this term. Now, when I do, here's how I'm going to write it. Like so. See that carefully? This multiplied by this. And now we'll add that to this multiplied by this. Here's how I'm going to write it. Like so. So that's one of the inner terms in FOILing. Okay, here's the other inner term. This multiplied by this. Like so. And then lastly, this multiplied by this, the last term, if you will, in FOILing. Like so. And now all of a sudden, instead of one dot product that I have to do, I've got 1, 2, 3, 4 dot products that I have to do. So right now the situation looks a lot worse than it was before. However, let's take a look at the dot products between all of these unit vectors. For example, take a look here at the first one, I dot I. So how do we calculate this dot product? Well, you just use the definition. We take the magnitude of the first vector. Remember that the magnitude of a unit vector is 1. And then we multiply that by the magnitude of the second vector, which is also 1. And then we multiply that by the cosine of the angle between the two vectors. What's the angle between a vector and itself? 0 degrees. Cosine of 0 degrees is equal to positive 1. So then therefore I dot I is equal to 1. J dot J is also equal to 1 for the exact same reason. So this term here is 1. This term here is 1. And now let's take a look at the other terms. For example, I dot J. So we take the magnitude of the first vector, 1, times the magnitude of the second vector, 1, times the cosine of the angle between the two vectors. What's the angle between I hat, which points along the x-axis, and j hat, which points along the y-axis? 90 degrees. Cosine of 90 degrees is equal to 0. So then therefore I dot j is equal to 0, and j dot I is also equal to 0 for the exact same reasons. So this term here is 0, and this term here is 0, like so. And now take a look at what is left over. What's left over is that a dot b is equal to the following. We have right here a sub x times b sub x, and then we have right here plus a sub y times b sub y. So when vectors are in component form, all that you do is multiply the components together and then just add them up. Let's go ahead now and apply that to the problem above. So for the problem above now, a dot b is going to be the following. First of all, we take the x components. So this 6 here and then multiplied by 2. Like so. And then we add that to the y components being multiplied together. 3 multiplied by negative 6. So, and you end up with 12 minus 18, which is equal to negative 6. So when you've got vectors in component form, finding the dot product is easy. All you do is multiply components together and then add them up like so. Okay, this is the necessary mathematical background that we need going forwards now on our next unit covering work and energy.